And so hypothesis testing, we had a couple different approaches. There was the classical approach, which is based off the number of confidence or the number of standard deviations from the mean. So remember, if you're doing that, you have to find your Z alpha level, and then if you would be, depends on the test, if you're doing left, right, or two-tailed. So if it's a greater than, you would look to see if the Z for your data is greater than the Z from the Z alpha, and if so, then you would reject. Less than, if it's smaller, you reject. Two-tailed, you have to divide that alpha over 2 because you have to put the percentage in both tails, and if you would be in that shaded region, you would reject. That was the classical. We also talked about p-value, which is a little more straightforward. It's just finding your probability. And when do you reject? If p is less than alpha. The one thing you have to watch on that is if you have a two-tailed test, what do you have to do with your probability? Multiply it by 2, because you have to take into account both tails. We also talked about doing it on the calculator. Do you guys remember where we went to? Stats test number 5. And that one does, it gives you both. It gives you the z-score so you could do the classical, but it gives you the probability, so it's easiest just to do it like the p-value test. Another option with hypothesis testing is to do a confidence interval. So if you look at your formula sheets, we have created confidence intervals before. Remember doing those when you have like plus and minus, so p hat, plus or minus, all that stuff, or you did them with x bar. So you can create a confidence interval, and if your value is in the interval, you would fail to reject. And if your value is not in the interval, then you would reject. So that's what we're going to look at first. It's a hypothesis test. You can't test it unless you have a null and an alternative hypothesis, so we would have to set those up. And this is all it's saying. If your confidence interval contains the null hypothesis, then we don't reject. If it does not contain the null hypothesis, that would be when we reject it. So let's take a look at one. In a 2009 study found that 34% of teenagers text while driving. A more recent survey found that 353 of 1,200 randomly selected teens had texted while driving. Does this suggest the number has changed since 2009? Use a 95% confidence interval to answer the question. So first we have to have the null and my alternative. What is my null hypothesis? Okay, and then the alternative would be what? Because we want to see if it has changed. All right, what else do we need to do? Criteria. So remember we need n times p times 1 minus p be greater than 10. So my n 1200 p 0.34 1 minus 0.34. That's 269.28, so that's definitely bigger than 10. The other one, our sample has to be less than 5% of the total population, and is that true? Yeah. Okay, so we checked our criteria. Those are satisfied, which means we can proceed. So next step, if we are going to test this, what do I need to find? P hat. So P hat we know is x over n, so 353 over 1200. .2942. All right. What now? Okay. If we're getting our z-score, we have to use the mean and the standard deviation, right? But this one, it did say to do the confidence interval, so look up your confidence interval formula. We're talking about a confidence interval for which one? X, we have two. Confidence interval for p hat or x bar, which one are we doing? P hat, so it's under chapter 9. Remember when we did those, it was p hat plus or minus the alpha over 2 times the square root of p hat, 1 minus p hat over n. So the reason I'm not doing the mean standard deviation is I didn't ask for the z-scores, I asked you to create the confidence interval. All right. From here, we have the p hat, we have the n. What's the one piece we don't have? Z alpha over 2. So that's the other component we need. Okay. We want a 95% confidence interval. So that means 95% of our data is in the middle. So 5% is left over. You have to split that over the two n's. So each n gets 0.025. How do we look it up on the table? We would look up, we need this z, so that all of that is below, so 0.975 is below. So you're looking inside the table for 0.975, or as close as we can get. And that one does work out perfectly. That is a 1.96. So our confidence interval is our p hat, 0.2942, plus or minus my z, 1.96, square root of p hat, 0.2942, 1 minus 0.2942 over n. So remember, interval should go small to large, so put the smaller one in first. Oops, I wrote n. What is our n? Thank you. So I get 0.31998 or 0.320. Could we have just built this confidence interval on the calculator as well? Yes, remember we did that before. Do you remember where you guys went? Stats, over to tests, and down to A, the 1 proportion Z interval. It should give us the same thing, maybe just a slight difference in decimals. So what we do at the end, this is a 95% confidence interval. So we are 95% sure that the real proportion falls between these numbers. My null hypothesis was 0.34. Is that in my interval? No. So if I'm 95% sure it should be in here, then, and this one isn't, what does that tell me? We would reject. Or if I asked you to describe what that meant, that would mean there is not enough evidence, or there is, okay. We're trying to prove, are we ever actually proving that the null is true? No, we're trying to prove the alternative, essentially. And if we fail to, then we just accept that. But this one would say we have enough evidence to conclude that the proportion is not 0.34, or the proportion is different today. Questions there? All right, so every time I have you checking criteria, and every time it's worked. But what do we do if it doesn't? Okay, remember our criteria, we have to check that so that we can assume it is what? Normal, which is what allows us to use that normal table. Way back before we had normal data, we had, do you remember what kind of data? When we had like the independent ones, and it was basically yes, no answers, a fixed number of trials. So we dealt with smaller sets. Remember talking about binomial data? I have failed. Okay, so if we can't assume it's normal, we have to go back to like the binomial data. That was when we had discrete, like countable, a fixed number of trials. We went to normal when we had continuous data or big enough sets that it would start looking normal. So, so if it doesn't meet the requirements for us to assume normal, then we have to go with the binomial. All right, let's take a look at it. In 2006, 10.5% of all live births in the United States were to mothers under 20 years of age. A sociologist claims that births to mothers under 20 years of age is decreasing. She conducts a simple random sample of 34 births and finds that 3 of them were to mothers under 20 years of age. Test the claim at the alpha equals 0.01 level. All right, so what is my null hypothesis? What is the alternative? Which she believes it's decreasing, so it'd be less than. So when we check our criteria, my n is what? Times p, 0.105 times 1 minus p. Oops. And that is 3.195, which is not bigger than 10. That's actually less than 10. So what does that tell me? This means it is not normal. Okay, we do not have normal data, so we can't do the z-scores. We can't do our probability from the table. We have to use the binomial approach. Remember, binomial, they have to be independent. So are all these her sample that she gathered? Is there any reason for us to believe they're connected in some way? No, so we can assume they're independent. We have to have a fixed number of trials. Do we have a fixed number? Yeah, we have 34. And there can only be 2 outcomes. Are there only 2 possible outcomes here? Yes, either they had a child or not. So this is binomial data. It's just not a big enough set of binomial data to start looking normal. So let's refresh. If you have forgotten what binomial looks like. So if you go back under chapter 6, where it told us that our binomial for finding a probability, it was n choose x, p to the x, 1 minus p to the n minus x. We also had a binomial table at the end of our formula sheet, but it was somewhat limited. The highest n on our table went up to 20, so would we be able to use the table? No. Okay, so now we need to figure out, what are we trying to find the probability of? She had a sample and found that 3 of them were under 20. All right, so do I want to find the probability? We know it's something with a 3. Do we want to find the probability that it's more than 3, less than 3, or equal to 3? So usually with the normal, we're not just finding equal to a number, right? We're finding more or less. Our alternative here, we're checking if it's less than a certain number. So we need to find the probability of being less than or equal to our 3. All right. So with binomial, you have to find everything separately. So we have to find the probability that 0, 1, 2, and 3. And unfortunately for us, we can't just read them from the table because our n was too big. So we can go to our calculator. Okay, there's several different ways to do this, so I want to kind of run through what we're doing here. The formula is n choose x. So for x equals 0, the number was, we had 34, choose 0. P, what is the probability of, in binomial terms we usually call it the probability of success. What's the probability that we're comparing here to? Yeah, it's like your null hypothesis, the 0.105. To the x, 1 minus p to the n minus x. So it's saying none of them had a child, 34 did not. All right, when we did 1, it was 34 choose 1. One of them had a child, so 0.105 to the first. That meant 33 did not. So this would be to the 33rd. Do you guys remember this? So usually, you don't necessarily have to write out this line, but just because it's been so long since we've done a binomial, I'm writing it out to kind of show you. Okay. So on our calculator, it's probably easiest just to do one at a time. If you do parentheses 34, and then if we went into math, probability, there's number 3, NCR. So that's 34 choose 0. P, so 0.105 to the 0. 1 minus p to the 34. And I get 0.0230. And once you have the first one, you can just bring it back and change your numbers. So now it would be 34 1, 0.105 to the first, 1 minus 0.105 to the 33rd, and we get 0.0918. Bring it back and do the second. So 0.1777. And one more for our third. So one of the downfalls of this, it's time consuming, especially if we had a bigger x value and we have to find all of these things individually. So if we add all these together, what do we get? Okay, so is this unusual at all? No. There's a 51.49% chance that she had the sample she did if the null hypothesis is true. So what would this tell us? Reject or fail to reject? Fail to reject. There is not enough evidence to show the proportion decreased. Okay. Would anyone like to see a calculator shortcut? Now that we've done all of our binomial, we've refreshed how to do it. Your calculator can do some of the binomials as well. If you do second, and then the bars button, this takes us into all the different distributions it can do. If we go down, there are two options: binomial PDF, binomial CDF. A binomial PDF would calculate one probability at a time. So if you chose that one, it's going to say, okay, how many trials? So if I said 34. P, if I'm doing the first one, we had 0. Or sorry, our P was 0.105. The X, so the very first one we found was when X was 0. And if you calculate it, it puts it into this formula for you. Is this the same thing we got when we did it by plugging in for the first number? Yeah. If you go into the second bars and you do binomial CDF, that is the cumulative. It gives you the probability of everything less than whatever number you start with. If you needed greater than, what would you have to do? 1 minus whatever number we get here. So on this one, we could say, okay, we have 3 trials. The probability was 0.105. The X, we want everything less than 3. So we'd have to put in 3. And is that what we got for our final probability? Yeah. So we can also use that shortcut to help. We're not going to have a lot of these problems that we can't do as a normal distribution. So it would be rare to have one that didn't meet the criteria and we had to treat it as a binomial, but it can happen. All right, that is the end of the section. So you guys have all of the homework for 10.1 and 10.2 now that you should be working on. Tomorrow we will start section 3.